All right. Hi, everyone, and welcome to my channel, Maths Made Easy with Terry in 10 minutes. Okay. So we are here to talk about partial fractions, and partial fractions is not really difficult. You're just breaking a whole fraction into smaller fractions. So this is similar to what you've done in arithmetic expressions or equations. For instance, if you have 17 over 20, right? It's the same thing as saying 1 over 10 plus 1 over 4 plus 1 over 2. So 1 over 10 plus 1 over 4, 1 over 2. Does that make sense? Now, if you add all this together, all this is going to give you this fraction here. So that means you can say that all these are partial what? Fractions. Okay, all these are partial fractions. So if all these are partial fractions, so now we're trying to then apply this to polynomials. And just to remind you, I told you earlier in my previous video that when you have a fraction like this, the top is the numerator and the bottom is the denominator. Okay, so then how do you now do this to polynomials? Let's assume you have something like x cubed plus 2x divided by x to the power 5 plus 1, and I want you to break them into partial fractions, so in smaller fractions. Okay, so usually what I always explain to students is that usually we have 5 rules, okay, or 5 steps to take to get your answer. All right, and I'm going to go through all of them now. All right, now the first thing you have to keep in mind is that the numerator of the given function must always be lower, of a lower degree than that of the denominator. Okay, so I'm going to write it down. So the numerator of the given function must be of a lower degree. So the key is lower. Okay, so not equal to. Okay, so it's not going to be not equal or higher, always lower. All right. Okay, it has always to be lower. Okay, must be of a lower degree than that of the denominator. So for instance, if you have x3 plus 2x divided by x7 plus 1, so you can see the degree of the numerator is what? 3. The degree of the denominator is what? 7. So then, therefore, you can use partial fractions here. But if, for instance, you have maybe x to the power 2 plus 1 divided by x plus 1, you can see the degree of the numerator here is 2, and the degree of the denominator here is 1. So you can use partial fractions directly. So in this case, the first thing you have to do is to first divide. Okay, you have to divide using long division. Okay, so when you have something like this, you then have to divide using long division. So I have uploaded a video on long division. So I advise you go back and have a look and try as much as possible to understand it before coming here. All right, because we're going to apply long division in several cases, especially when we have the numerator that is higher than the denominator or equal to. Is that okay? So if, for instance, like in this case, right, what you have to do first is that you have to do long division. And I told you in the video that you have to then leave your answer in the form of quotient plus the remainder over what? The denominator. So now is this part that you then have what? Is that what you now use for the partial fractions? Okay, so when you've broken down into that, then you now break this into the partial fractions. Okay, don't worry, I'm going to solve questions on this so that it will make more sense. But basically, that is the first thing to keep in mind while solving. Now, the second part here is when you've done that, then the denominator of what you want to express, you have to break them into its prime factors, okay? So basically, you have to factorize, all right? So you have to factorize the denominator into its prime factors. So I also have a video on something like quadratics, polynomials, so you can go back and have a look. So let's say we have something like x squared, or let's say we have x plus 1 divided by, so we have x plus 1 divided by x squared plus 5x plus 6. Now, the degree of the numerator is 1. Degree of the denominator is what? 2. So we can use partial fractions here. Now, when we've done that, the next step that you have to do is to break this down into the prime factor. So that means I can break this down into x plus 1, x plus 3, x plus 2. Can you see? So I've broken the denominator into its prime factors. Okay. So that's the second step to do. So try as much as possible to review my previous video on quadratic equation, polynomials, so that you can know how to factorize. Is that okay? All right. So when you're done with this, the next step is that you then have to write the partial fractions, okay? For, or you better say, write one partial fraction for each of the prime factors used, okay? So next one is to write one partial fractions for each prime factor used. Okay, so usually based on the type of factors. Okay, so usually based on the types of factors. So we have about 4 types. So don't worry, I'm going to explain each of these to you later when I start solving an example, okay? So we have about 4 types. We have what we call the linear factor. So the linear factor is usually in the form of ax plus b, okay? So you write the partial fraction like a over ax plus b, okay? The second one we have is what we call the axb2 factor or axb squared factor. And the axb squared factor, you're going to write it as in the form of a over ax plus b plus b over ax plus b all squared. Is that making sense? Then you also have what we call the ax plus b3 factor. It's going to be the same thing, but you're going to have an extra partial fraction. So it's going to be plus b over ax plus b squared plus c over ax plus b cubed. Then the last one that I will talk about in this series is what we call the quadratic factor. Quadratic factor. So, as you know, quadratic factor is in the form of ax squared plus bx plus c, okay? So these are usually occurs where you can't break down the quadratic equation into any of the linear factor or the ax plus b squared factor. Then you then have to make it be in the form of ax plus b divided by ax squared plus bx plus c. Okay, so this is the third rule. So when you factorize the denominator, then you now have to write one partial fractions for each prime factor based on the type of factor, all right? Now, when you've done that, and you've determined that you have written that correctly, Now, the fourth step that you have to take now is to multiply both sides using the denominator, okay? Because it's important that you're trying to get an equation that you can equate to get the unknown. So usually what you do is that you multiply both sides in the denominator of the initial fraction form from step 2, okay? So this step 2 here, where you factorize the denominator, okay? They have to multiply both sides by that denominator. So number 4 is to multiply both sides using the denominator. Okay, of the initial fraction from step 2. And you then simplify. So I'm going to explain this step. It's just basically multiplying both sides with a denominator. And when you're done with that, then that is when you now have to then do what you're looking for by finding the constant term. So you have to find the constant term. So it could be A, B, C, D, okay, etc. It could be A, B dependent, okay? Now there are 2 methods to use to find the constant term. Now there are 2 methods. So using any or both methods. So there are 2 methods I usually use to find the constant term. The first one is what I call the substitution method. Okay. Now, the substitution method is usually the quickest, but it's limited. Okay. So it's usually the quickest, but limited. Okay. Now, with the substitution method, what I do is that you look for the x values that where you substitute is going to cancel out, make 2 of the unknown or 2 or more, just leaving 1 of the unknown. So that means you substitute a value into the expression such that all but 1 of the unknown will become 0. Okay, so basically that's what you do. So the first thing is the first thing usually is that you then look for x values that when you substitute, other constants will be 0 except 1. That makes sense? Then when you've done that, you then repeat it till you find all the constant terms. So basically, so I can write it here. So the first thing is that you look for x values. That's when you substitute. Okay. Other constant except 1 will be 0. You will be left with 1 term. Okay. Then when you've done that, you then repeat it till you find all the time. So the same thing, you keep on repeating, all right? So you then repeating this step. So repeat till you find all the constant term. Okay. Then when you've done that, then you can now go back to step 3 and with the calculated constant term, and you then rewrite it. Okay. Remember, step 3 is where you are writing them in the form of their partial fraction. Because at this time, for instance, I know my A, I know my B, I know my C. So I'm going to rewrite the expression using this. So that's what I'm just trying to say. So you're going to rewrite step 3 with the calculated constant term. So you have to rewrite step 3 with the calculated constant term. So, but like I said, this is it's a very quick method, but it's very limited because there are some cases where you can use substitution method to get the answer. All right. So in case this fails, usually the next step I always suggest, the next method is this coefficient of x method. Okay, so it's just a coefficient of terms comparison method. Now, this method is going to be very long. Does that make sense? So it's very long, but it's always going to give you the answer. All right. It's always going to give you the answer that you're looking for. Okay, so I'm going to write it as the coefficients. So that'll be the second one, coefficient of term. Okay, so it's called the terms comparison method. Okay, like I said, this is the longer, okay? It's very long. It's longer compared to the previous one, but it's not limited. Okay, so that means no matter the question, you can get the answer. In the worst case scenario, you might have 3 simultaneous equations that you're working with, okay? So what you just do here is that you compare all forms of each side, okay? So you first compare all forms of each term coefficient on both sides of the equation. Then this will now make it to not be, you'll be led to derive a new equation having the constant term. After that, you now solve using simultaneous equation to find the constant term. And then you rewrite step 3 with a constant term, okay? So the first thing you do is compare all forms of each term. All right. So remember the keyword is the each, okay? So each term, the coefficient that each of them has, okay? So you compare them. Then on both sides of the equation, then after that, it will now, it will now lead you to derive a new equation, right? So now you get new equations. So, but the new equations will be having the constant term in it. Then when you now have that, then you now solve using simultaneous equation. Okay, so to find the constant term. So then after you found the constant term, you now go back, okay, to rewrite the equation in step 3. So you now go back to rewrite the equation in step 3. I know that this will be looking a lot, but it's really simple. The reason why I'm just writing all the steps out is that, so just in case, when you've perfected how to solve it, you don't need to know this, it just comes naturally. Does that make sense? But here I'm going to be using these steps to explain, so you can use it to practice. But when you know what to do, it will just come naturally to you, okay? So you're gonna rewrite step 3 with a calculated constant term. Okay. Then, or like I said, you could use the third method, combination of both methods. So you can either use the quotient of terms comparison method, or you can use the substitution method, or you can use combination of both methods. But personally, I always prefer the combination method, okay? So personally, I prefer the combination. So what I do is I start first with the substitution. Then when I can proceed with the substitution, then I then complete it with the quotient of terms comparison method. Is that okay? So I start with substitution method. Okay. So when I start substitution method, then when I'm done, or when I can proceed further, okay? Then I now move to quotient of terms. All right. So usually I use both methods. So the combination of both of them is usually easy for me. All right. So but in this series, I'm going to talk about, I'm going to use combination method. Is that okay? So I'm going to first start with substitution. Then when I get to a point that I can move forward with substitution, then I now move to comparison method. All right. So that is that for that. So from next video, I will start solving some examples. All right. So, but generally what I've said is that I've just introduced to you the 5 rules, okay? The concept of the 5 rules. So the first thing is that if you have a partial fraction, so what we're trying to do with partial fractions is that we have a complete fraction that we're trying to break into smaller fractions. Then when we're done with that, I told you for polynomials, there are 5 steps or 5 rules to take into consideration. The first thing is that the numerator must always be lower than the denominator. All right, the degree of the numerator must always be lower than degree of the denominator. And if it's not possible, you have to then use long division. Then when you've done, you factorize the denominator. Then you now write the partial fractions as each of the prime factors of that denominator. Then when you do, after that, you multiply both sides by the denominator. Then you now find a constant term. You can either use the substitution method, or you can use the coefficient of terms comparison method, or a combination of both. But for this series, I'm going to only be using a combination of both methods because it's faster. Remember, I told you substitution method is always the fastest. Okay, so I can use that first. Then when I'm stuck, I'll now use coefficient of terms method. All right. So that is that for this series. Sorry, for this video. Next video now, I'm going to start solving questions. So I'm going to start solving each of this. So I'm going to pick examples from the linear factor. I'll pick examples from the ax plus b2 factor, ax plus 3b factor, and quadratic factor for this. And that will be the end of the video for this series on partial fractions. Okay. So as usual, I'll see you in the next video. And if you have any questions, feel free to let me know or put it in the comment section and I will get back to you. All right. Thank you very much.